let's see what we're going to do with our Hershey's Kiss lab today. Yesterday, we ended with the interval that you created. And so you were estimating the true proportion of times that all Hershey's Kisses, land on their base. Okay, so that's the population amount that you were estimating with your one sample. All right, so I got this answer here. So I am 95% confident confident that the true proportion of times all Hershey's Kisses land on their base, bases, um, is between 22.8% and 41.2%. Okay, and that's what you had also done in the homeworks, which I'll show that for you so that you can check yourself and see how if you did well on making your and computing your intervals from yesterday. Now, let's move on. Let's see what happens next. So, I want you to actually make your interval now. So here is my interval. My interval that's centered at 0.32. So that's where you put a dot. Okay? So you put a point. That is your point estimate right there at 0.32. And then you draw this line at the lower bound and the line at the upper bound, and you're drawing your whiskers to those edges. And that is representing the range of plausible values that you think estimate the placement or will estimate what that true proportion of the population is. All right. So I also went ahead and I put on my other friends' values. So if you got to do this, put yours and some of these on there as well. But you can you see that they're kind of located in the same general vicinity? And also that their whiskers all are kind of covering the same general amount. Like, for example, so this is interesting what I see here. I see that it looks like this amount right here, and I should have done that in a different color. But this amount right here seems to contain or be captured by all of the intervals. So that's something that we're going to be considering is looking at this line that is in all the intervals. It looks like from here to here, it's going to be covered by all of the intervals. Okay. All right. So see, that's of interest to us. That, as I've taken many of these intervals, has just kind of narrowed even down my field of study even more. Okay. All right, so let's take a look at some other things that we're going to be talking about. And this is what I had just written on the other page, that I'm 95% confident that the true proportion of all Hershey's Kisses that will land on their base is between 22.8% and 41.2%. All right. So now we are going to merge the samples that we got. So that makes a sample of 400. And so what I'm even going to do, and I'll show you what these look like. I'll put a picture up. I haven't gotten these graphs made, but I will certainly post that in a small little video talking about them. But I collected all the data from yesterday. And then I'm going to get the value for 4 of them combined. Okay? So once I get that value for 4 of them combined, I now have a sample size of 400. And so let's take a look at that. So look at what happened. So sample size of 400. The average of my 4 friends, or the 3 friends and myself, was 0.33. And so then here was this margin of error, the critical value, the Z star, times that standard deviation. And so look at this interval from 0.28 to 0.38. So let's look at that up here. It is this bottom interval that I have. So if you notice, this bottom interval looks a tad bit different from the others. What is interesting about this interval? I can graphically see, and if we had a whole bunch of them, it'd be even more obvious. It is narrower and skinnier than the others. So it definitely has a smaller margin of error. Why? Because when we had a sample size of 400, that made this standard deviation be divided by 400, which made this standard deviation smaller. And then hence the margin of error was only 0.046. Now, if you recall, my margin of error from yesterday was 0.092. So right at double the amount. Okay, there's actually a reason that it even came out to be exactly double. And so we'll talk about that here in a minute as well. Okay, so take a look at this. Compare them. Are the individual proportions of the confidence interval different from that of your group? If so, how? Yes, I can see that they are wider. So I'm kind of answering what I've already talked to you about. Yes, they are wider. And then what about the widths of the, are the widths of the individual ones different from each other? Just a little, not very much. So like if you went and looked at all of the margin of errors that we had for everybody's, they'd be a little different because of the different p-hats. Because look up here, see this 0.33 here versus having whatever else that p-hat is. That's going to change this numerator slightly. Not a ton, especially compared to how much that sample size change of 4 times as much affects it. Okay, so in essence, what I'm saying is that all of these ones up here are very much more similar in size than this one down here at the bottom that had a sample size of 400. Okay, now let's then take this forward. How did increasing the sample size to 400 affect the width of your confidence interval? So we've already seen that. It definitely made the interval smaller because that standard deviation is smaller. All right. What statistical concept or principle, what did we just finish, what unit did we just finish talking about? Does this remind you of? What did we find out with our sampling distributions? Remember that as the as the size of the sample increased, that sampling distribution got smaller and smaller. So that was the exact same tie-in. All right, now. So it says when you are done, draw your group's confidence interval on the group chart. And so I'm going to show you, again, a picture once I get them made of the individual confidence interval chart and the group confidence interval chart. So we'll look at that in a different video after I get those made. So now, why was that group's standard deviation effectively half of what all the individual ones were? We multiplied the sample size by 4. Why did that make the relationship 1/2? Well, let's look at that. Here it is. This is a big deal for you to understand. When the sample size went from 100 to 400, it increased by 4 times the amount. So look here, compare. Here is the formula for standard deviation. Compare it to this formula for standard deviation with 4 times the n. Okay? Now, let's take out this 4 and see what happens. Pulling out the 4 from the denominator makes, in front of this here, 1 over the square root of 4, which is 1/2. So there is why it was basically exactly 1/2. Therefore, increasing the sample size by 4 reduced the standard deviation by 1/2. If I increased the sample size, let's do it easy. If I made it 9 times larger, what would that change about the standard deviation? 9 times larger would be 1 over the square root of 9, which would make the intervals 1/3 the size that they previously were, and so on. Okay. Now, we're going to elaborate on this next part at a later point, but I want to start planting these seeds now of these ideas. And I think that, so some of this wording and some of this thought process of this is kind of a little abstract and a little bit crazy right now. But we'll continue to revisit this so that it eventually will kind of feel a little bit more natural. So, we're actually going to talk about this. Okay, well, first, let's see here. Which of the following do you think is true? More than one may be true. So we're going to talk about these statements below. Consider this thought as well. Does the true population proportion change? So is this red line a value that changes because of you getting different intervals and such? And this is a big deal. No. That line, that population amount is set. I don't know what it is, but it's there. It does not change. All these intervals around it are varying because of sampling variability, but that line doesn't change. Okay, that true population proportion does not change. That's the big deal. Okay, so I want you to read that comic strip down there. It actually plays right into all of these questions. So it's kind of, and we'll see the tie in here in a minute. So the first question, or the comic strip, is these guys looking for this map, and this person says, I got the instructions from my statistics professor. He was 80% confident that the true location of the restaurant was in this neighborhood. So there's actually a problem with this statement, and so we're going to talk about that. But I think kind of having this concrete example will make it a little bit more sense. So let's take a look at that. This was something that was very confusing to me for a long time when I first started doing this. Okay. In the comic to the side, is there an 80% chance that the restaurant is in that neighborhood? And that answer is no. No, there is not an 80% chance that the restaurant is in the neighborhood. So let's consider this analogy. Think of the neighborhoods, all the different varying neighborhoods in the area, as your intervals. Okay, the neighborhoods are your intervals. And think of that restaurant as that true parameter that you are trying to locate. Okay, so if you look at this picture, is there an 80% chance that this red line, is there an 80% chance that this red line is in one of those neighborhoods? And that answer is no, because this red line doesn't move. We talked about that. It is set, it is firm, it is in place. It's the intervals that we are wondering about capture, contain that population amount. So it's the direction. It's not about if the population made it into your interval. It's about, did your interval can capture the population amount? Okay, I'm going to say that again because that is very tricky. It's not about the probability or the chance that this line lands in your interval. This line does not move. The line is set. It doesn't change. It's not about the chance of that line landing in your interval. It's about, is the interval you made, did the interval you made happen to contain that population amount that is set in stone? Okay, so again, this is an abstract concept that has just taken a while, and it always makes me have to still stop and think. Okay, so let's keep going. And as I said, I introduced this. It's a little wonky and kind of weird, but we keep continuing to revisit it as we go through our unit. So here we go. So here's what I wrote. The restaurant doesn't move. So there's not a probability or a chance that the restaurant is in the neighborhood. Instead, there's a probability or chance that the neighborhood you picked contained the restaurant. Okay. So can we say oh, you know what? I wrote 95% confident. I guess I should have been writing 80% the whole time. Okay, so don't worry about this percent. We are 95% confident that the true proportion will fall in your interval. Again, what's that saying again? We are 95% confident that the true proportion is going to move into your interval. No, same thing as above. No, we're 95% confident, or in this case, it should have been 80% confident. Sorry about that. That the interval was in a place to capture that true population amount. Okay. We are 95% confident that your interval will include the true proportion. Okay, I think that's see, I get confused still. Okay, we are 95% confident that's your interval. So what are we talking about? We're talking about if that interval is going to contain it, not if it is in the interval. Does that interval contain it? That's what we're talking about. Yes, we are 95% confident. That confidence level is about how confident you are that your interval is in a location that will catch or contain that true population parameter. Okay. Before we take this sample, there's a 95% chance that the confidence interval we create will include the true proportion. So the confidence interval, okay, so this is us making the confidence interval. Is there a 95% chance that the neighborhood we pick or that the confidence interval we make will capture the true proportion? So I'm liking that one. That one is good. But I think this one is a little on the flip side. After we take the 95% chance, I wish I would have changed this around to say a 95% chance that the true proportion is in the confidence interval. That's what I was going for. There's a 95% chance. So here I am still tweaking this lab. There's a 95% chance that the true proportion is in the interval. True proportion is in the interval. That's where we get bad, when we're talking about that true proportion being in the interval. Okay, that's what I was going for there. No, this implies that there's a probability that the true population parameter may or may not be in the interval we created, meaning the true population parameter sometimes is in the interval or sometimes not. This is implying that the true parameter moves and it doesn't. Okay. We'll keep on visiting that. Those are kind of crazy. So now, I think that brings us to a close of our lab. Here was the chart for you to check your intervals, and we'll continue on. I'll go ahead and do another short video of you being able to check your assignment here to see if you got your computation correct. And there's another short little video of a little bit to add to the end of this lab. All right, so we'll see you in the next video.